Which unit do you have questions?
Unit 16. And then it's the first standard exercise. Number 2's were problems. So let's see.
What you do? And we have this thing. So basically what's the formula for, how do you find the current?
I'm assuming B equals I R.
Okay. So we know the resistance R of the loop that I didn't draw. So we need to find current, right? So we need potential difference. So how do you find potential difference?
Do you use a integral like box?
I think somewhere in the lecture they gave you a formula for motion of yeah, they gave you a formula. EMF is equal to VB out.
Mm-hmm.
So EMF is equal to L. Tell me which one is well. E is obviously the field. What about V and what about M?
Yes. Velocity and L is like the length of the wire that's determined the field.
Okay. So we have the velocity.
Mm-hmm.
we have field. I think they give the field, right?
Yeah.
So we need to know which L we're talking about with the potential difference. Right? Okay. So to know what L we have, we need basically to know how the current situation, how this will. So give me your number.
Velocity is 31 centimeters per second, and time is 0.741 seconds.
What was that?
0.741.
7.1?
Yes. Oh, no, 714, sorry. Seconds.
What's the?
L is 17.1 centimeters.
What about S1 and S2?
S1 is 3 centimeters, S2 is 6.1 centimeters.
So initially we have S1 being here, right? At the x equals 0. So where would this rightmost part be in this time? How do you find that?
Multiply time and velocity.
Yeah. So what would that be?
22.134.
So we say x right is what?
22.134. So it's like outside of the magnetic field?
Right. So it's exiting the field, right? So we have our rightmost edge already. Well, if this is 17.1, the coordinate, then here the rightmost front is at 20. What about, well, we know that S1 is 3 centimeters. So 22 minus 3 is roughly 19, right? So there's your. So it's still greater than 17. So this little step of the loop is already outside of the field part. So you have it like this, right? And it's going that way. And then S2 is 6 centimeters. So we see that it's going into the field, right? Like this. So this part is not in the field. Some of S2 is in the field, but not entirely. Okay?
So you, can I ask a question?
Yeah.
So you only consider the length of the part that is in the field, because in working the problem you need to know the length of the side.
Okay.
Yeah. So.
We didn't get there yet.
Okay.
Okay, then let's talk about L. Let me pull this small L because we have bigger. What is this L?
I thought it was S2. I'm not sure if that's.
Why is it S2?
That's the question I was asking.
Why? No, you explain me.
To me?
Yeah.
Yeah, I think the L will be the portion in the field, because with this other.
Which one? This isn't the field. This isn't the field. This
Yeah.
isn't the field.
Yeah, it will be the height.
Why?
Have you any idea?
Oh, does it have to be like perpendicular to?
Yeah, because you have, well, right angle, remember? So you have, what was the thing? What was the right angle? The cross bar. With the forces and everything.
The force equals I.
So, yeah, if you have current in this region, it's going to be parallel to the velocity vector. So your cross product is zero. Right? You don't, this doesn't have potential difference in it. Potential difference comes from just this region. You have potential difference between this part, this side, this point, and this point.
Because it's perpendicular to the current.
It's perpendicular to the field and the velocity.
Okay.
You need the three perpendiculars.
Yeah. Yeah.
You
It's
have
perpendicular to
force that would separate the, make the potential difference. So yeah, this indeed, there's two
yeah.
there. So we have V, B, S2, and I is equal to this EMF over resistance. Equal V, B, S2 over. But we just talked the magnitudes, right? What about the direction?
Yes. The direction of the current. Yeah, if the B field is coming out of the screen. So the direction of the current will be in the counterclockwise.
Why?
Because the B field is out of the screen. So the right hand rule is like this. Yeah.
Okay.
But what about when okay, let me give you another. This is the right answer, but the reasoning is a little, I don't think it can be applied in any case. If you had your loop, you entering like this, what's the direction of the current?
It's opposite.
I think
But I thought the B field is there, so current will.
yeah. That's another thing. I think the direction of the current will be on the opposite.
Why?
Is because when the loop is entering a field, the once the direction of the B field is in a particular direction, when the loop is entering, the field that the loop will create will be opposite to the direction of that B field that is coming.
That's right. Because loops like to, think of them as being conservative. They don't like change. So the loops try to keep things as they used to be. So So when the loop is just entering, it didn't have any field enclosed within it. So when it's entering, it doesn't like field. So it tries to oppose the field that it's entering in and zero it out.
Yeah, I read.
So when it's entering, it creates current in such direction that its induced field is opposite to the one that's being forced on. When it's exiting, it's already used to having so much this field through it that it's okay, I just want to keep it as it used to be. So it tries to enhance it back to the field where it used to be. Tries to keep things constant all the time. Just think of it as it's always against the change. It's like a conservative. Doesn't make changes. Like an old thing, like old things. They want to keep things as they used to be when they were young. So yeah, indeed, when it's exiting, it tries to keep the view in the current is in the counterclockwise direction.
Yeah, I had a problem with changing from Tesla to Tesla meter. There's some problems here that you have the answers in Tesla, but then they are asking you to write the ones that you put in the box in TM, got T-M, I think it's Tesla meter.
So that box. Answer our questions.
That's what I'm looking for. It's homework number one. Okay. Homework one, the second part, the second question.
Which unit?
Unit 15. Unit 15, number 2.
No, show me the upper part. A solid cylindrical conducting shell within a radius A and outer radius B with its axis aligned with the axis of shell. It carries uniformly distributed current I in the positive z direction. An infinite conducting wire is located along its z-axis and carries current I1 in the negative z direction.
So I solved this one, I got it. But in 2, I solved 2. And it's asking for the answer in this. So is this Tesla meter? This TM? Because this is Tesla. That is one. But I
Well,
found
you're integrating V dot here.
Okay.
So when you integrate DL, so you'll get DL. So the V is in Tesla.
Hmm? Yeah, so I'm thinking about so we can go over this and see. Yes.
You want that? You want me to go over that problem? So we need to integrate B dot dl from B to S. What's the coordinate of this?
Coordinate of S is, let me go there. It is 6D
6 or 0.6?
point 6, point 6D, point 6D.
So what do you suggest that we do?
What do I suggest? Yeah, the first thing is d dot dl is equal to mu times I enclosed. I mean mu times I enclosed.
What are you including?
Hmm?
You don't have a. You're not including anything. You don't have a. Surface that's including anything. You're just. You just need to go from P to S somehow. You don't have a closed surface to enclose current. Do it.
I'm a bit confused on that.
Well, you can enclose something if you have a closed surface, right? In this case, you're just following the arc, and well, not really. You just have 2 points. They're not enclosing anything, so you cannot. Well, maybe you could find a solution that's enclosing, but there is an easier one without enclosing anything. I know what you're trying to do. You're trying to do mu naught I enclosed. But the thing is that is a closed loop interval. The sign with
Yeah, that's right.
But you don't
And then I also took into consideration the angle. I found the fraction of the angle of the cycle.
Yeah, you will need to.
Yeah, and I multiply that. Okay, yeah.
You can just integrate. You, I suggest that we break this PS interval into 2 intervals. One is along the arc from P to R, and then from R to S. Because we have, when we go from P to S, the field is not uniform. So we have P itself as a function position, which is a hard function. We don't want to deal with that. It's easier to just consider this and just where the field has the same pattern over this interval at every point at this interval, and then at every point at this interval there is a pattern, maybe a different pattern, but still we know the behavior. So we do this integral from P to R of B dot dl plus integral from R to S of B dot dl. Now, what do we do? What can we notice about one of them?
I think one of them would be ignore because it's like perpendicular to the plane field. Like from arrow to S.
Yes, I remember in the pre-lecture you had this.
Yeah, it was in pre-lecture.
This thing. Something like that.
Yeah.
So when B is perpendicular to DL at all points along the segment, then your dot product becomes zero.
Zero, yeah, that's what I.
Right? So here, you're moving towards the center.
Yeah.
So this will be zero there. So we just have to go with that. Right? So how do you determine the field there? What did you have to find that part one?
want to integrate.
What did you find in part 1? Yeah, you found the y component of the field at point P, right? And what's the direction of that field?
Mm,
Give me your numbers for I1 and
I1 is 5.3, 2.3 ampere, and 5.
Say it again.
I1 is 2.3 ampere, and I2 is 5.3 ampere.
Sorry.
5.3.
So let's say that out of the board is the positive z direction,
Mm-hmm.
right?
Yeah. Yeah.
What's the sign of enclosed current at point P? What direction? Out of the board.
It's out of the board.
Okay.
Yeah. So it's
So
positive.
your total current is out of the board. Hence,
Yeah, because I2 is
B
the.
field is up
Yeah.
entirely at point P.
Yeah. So it's positive. And I2 is the biggest current.
What expression did you get for field at P?
The field at P,
Yeah.
I got positive direction.
Well, you had to find it numerically. What was the formula that you used to calculate it?
I use mu naught. You mean part one? In part one?
Yes.
Yeah, I use mu naught I enclosed.
Okay.
Yeah, that's what I use.
What is I enclosed?
Huh?
What is I enclosed?
I enclosed is I1 minus I2.
I1 minus I2?
Yeah.
Well, we agreed that I2 is in the positive direction, right?
Mm-hmm.
So I2 minus I1.
Yeah, yeah. But at the end of the day, you still use the positive sign.
Okay. Well,
because I2
to get
is
it
bigger.
positive numerically, you'll see that this is greater than that.
Yeah.
So if you subtract I1 from I2, you'll get a negative result.
Yeah.
Sorry, you'll get a positive result if you subtract this from this, right?
Yeah.
So I2 minus I2, well, it doesn't matter. Okay. What's in the denominator?
The denominator is 2 pi p. I use p because it's the direction from the center to p.
Well, D.
Yeah, d.
Okay. Do you know what field we have at point R?
Point R.
It's the same field, right? Because it's like the same distance from the center. It'll just have different direction components.
Yes. But the magnitude is the same, right? And all the way along the circle centered at the origin.
Yeah, the b field.
And with the D as the radius, right? Which is what you kind of want to listen to from, right? So if you're going from P to R, our B is independent of the distance toward this because the distance to the center is constant. So that's the B field that we want. Okay. So it's mu naught I2 minus I1 over 2 pi D. You see that B is independent of our path, right?
Mm-hmm.
And so we can take it out of the integral. Well, it's also perpendicular to the. Remember when we were trying to determine the direction, we were using the right angle. And field is always tangent, right? So our dot product is always just B times field, right?
Yeah.
Because the dot product is of A dot B, for example, is A times B times the cosine of the angle between them. In this case, a angle between them is 90.
Yeah, 90.
Sorry, 0. Always 0.
It's,
It's perpendicular to the radius, right? But
Yeah.
not to the path that we are traveling. So angle is 0, cosine 0 is 1. Hence, this dot product just becomes b times dl. B is constant, we can pull it out of the integral. Right? So right now we have b times the integral of dl from b to r. So we just write it. So we just need the length of the path that we are going over. We're traveling by, which is the r, right? Here.
yeah, PR. That's the length. So
How
to
do you
find the
find
length,
r?
the angle is the angle between there is 45. So I put 45 as a fraction of 360.
How do you know that this is 45?
I think it was kidding.
Was it?
Yeah, because our coordinates are 45 degrees.
Yeah, because well, here x coordinate is equal to y. And yet alpha is 45. But the general arc length formula is just the radius times the angle and radius. Right? So d is alpha. You know how to get that? Okay, so the entire circumference is 2 pi r, right? You need just alpha out of 2 pi, right? So this is per 2 pi
Yeah,
for the whole circumference.
which is 360.
You're taking just this portion. 2 pi goes away.
And times 2.
Make sure this is in radians, not in degrees. So d. That's all. And so this is field. This is length. Well, this is like meters. Tesla meters, radians, they are conventional. So you don't get your Tesla meters from here.
So the D is what we use.
D is the x coordinate.
Yeah. B times
Radius of the circle.
Okay.
You're for physics too, review?
Huh?
You're for physics too, review?
Yes.
Do you have questions?
Yeah, I got some similar question with the right hand rules.
Give me a second, I'll finish this.
Sure, sure.
Does that make sense?
Yeah, that's what I'm trying to. So the alpha is determined from the arrow coordinate, the x portion of the arrow coordinate.
Well, you can look at this coordinates of these lie along the same. Oh, you're also given coordinates of point R.
Yeah. It's zero, 0.707. Yeah, 0.707.
So you consider x coordinate is equal to y coordinate?
Yeah.
So x coordinate is given to y coordinate and it's a right triangle. Happens only when alpha is vertical.
Okay. Yeah, but what I'm saying, like, if you see like 0.707 is something like 45 degree of a cosine 45 degree.
Well, it's on.
So is that another way you can?
Yeah, it is. Well, the thing is that from these coordinates you can find the tangent, I believe. Right? Usually you find the tangent.
Yeah.
They're just giving you
Yeah.
everything in terms of d. If d, for example, they just put 2 in here, and this would be 0.707 times 2. So that would be 1.4 something. It's not as clearly
Okay.
cosine.
So you can just use your tangent to find the.
Well, I'm just saying that in this problem they just give you everything in terms of d, right? So it's you can see that this is cosine and sine of 45. But if they give you a different number, then you will not see it as clearly. But yeah, it's cosine and sine. Also. Well, because this is same as this. It's radius. It's d, right? So if you have, for example, x coordinate over the hypotenuse, that would be the cosine of it. So 0.707 d over d, 0.707, which is square root over 2.
Okay.
Well, what I'm saying, yes, you're right, but, well, I'm just worried that you might get confused
Yeah,
if you get a different number.
Myself, that's why I'm trying to craft the strategy in deriving the angle. Yeah, without just predicting that since the arrow coordinates are 0.70 d, 0.707 d. So
Usually you can just say that y over x is tangent, right?
Yeah.
Y over x
Yeah.
is tangent.
Yeah.
So in this case it's 1.
Okay.
And same going for you.
Okay. So you're just going to say x times the x coordinate times d and the y coordinate times d, and you find the angle.
Yeah.
Okay. That's one.
What's your question?
Actually, I forgot. I watched the lecture series, maybe. I think this. I mean, I don't know why this the B go out of the screen because I think the eyes go this way. It should go this way.
It's going out of the screen here.
Yes.
Isn't? Oh, I see what they're doing. So they're marking it as V1. So it's
So always
field
for
produced by I1 at this point.
Okay. And also for this one, I mean, how can I use the right hand to figure out the force direction? Yeah, I know it should be perpendicular to the.
Let me cross over
Sure.
So he, as a negative charge minus q traveling about here, the field is here. And they're showing that force is out of the field. What's the formula for force? Using the cross point.
Q way B, right?
QV cross B, right?
Yeah. QV.
So from this formula, you can figure out what to cross with what. Because you with the right angle. So
You said,
if you have this thing, you can see that your fingers would be curling from B to B, and the thumb would give you force. So
yeah,
B cross B will give you
yeah,
the force.
that's sometimes I think there's I don't know what's that called. Do I need to like curve my fingers?
Mm-hmm.
Because
So
I don't know which direction I'm gonna go, like this way or that way.
this is your B, right?
Yes.
So if the particle was positive, then you would go V
Yes.
cross B, and your force is in that direction.
Oh,
Right?
this is negative, so it's
But it's negative, so you take V to be opposite, so that would help. So V cross B,
uh,
this is the direction of the force, which is coincides with this one.
maybe.
Yeah, yes.
Well, also you can try to think of it in terms of, if you take V cross B as it is, so the cross product gives you the vector, right?
Yes.
So V cross B as it is, V cross B gives you inside. Q is negative, so minus that vector.
Oh, it's
Minus that vector that you put inside, so it's outside,
yeah.
if that makes sense.
Yes, sure. There's another question. It's from the exam, previous exam. Like this one, I think the professor talked about this one.
Yeah,
Sure.
it's not so hard.
Yeah, I still got
Picture below shows a cathode ray tube in magnetic field. A beam of electrons is produced at the cathode and travels with a high velocity towards the fluorescent screen, conducting the magnetic field. The beam of electrons would hit the screen at the center. And the orientation of the magnetic field is in the negative y direction is shown, at which of the points of the screen would the beam arrive. Okay. So it arrives in the center if we don't have any field. And if the B field is down like this, then what's going to happen? Electrons would experience force on them, right? So we know that, yeah, okay. Electrons are traveling this way, right? In the absence of the field. Where would the force point if we have field pointing downward? So let's look at it from here. So let's say we're looking, we have this. This is the screen, and behind it is bar. Is the
It's coming out of the screen.
yeah, the cathode.
Okay, cathode is coming
So
out.
electrons are traveling towards you.
Yeah.
And we set up the field down. So what's happening to the electrons?
Mm-hmm.
V cross B. But V is for, we have electrons, right? So V cross B. So electrons are experiencing force in that if we're looking at this picture.
Yeah, but
in
if,
that direction.
where is the V going? Where is the V pointing in this case?
Well, electrons are flying towards the screen, but we have electrons that are negatively charged. So we take the opposite direction. B. Or we can say that, okay, it's electrons, they're flying towards us. So B cross B gives us negative force. Well, okay, this product, this cross product, gives us the vector in this direction. If we multiply it with the negative charge, field would be, force would be in that direction. So electrons are experiencing force in that direction. So the beam would deflect towards here.
Yeah.
Right? So I'm making here.
Yeah.
So that's why that point is
Mhm.
like largest force.
Hmm? Say it again.
That's why that point has the largest force, right?
Largest force?
Yes,
I don't think it is.
no, I mean this question is ask for which one has the biggest force, right?
Yeah, because the point with
It's
the biggest
asking-
force is where the cathode will go.
At which of the points on the screen would the beam arrive? So it's asking, the beam is narrow usually, so that it projects into one point, right? Without the field, they would be just traveling straight. If you introduce the field, the electrons would experience force, and it would deflect the beam this way. Because force is in that. It's pulling them away from the straight.
Thank you.
That makes sense?
Yes, yes.
Let me see. I think I need a ticket. Okay. Because the one on the exam question sheet, practice question sheet is not clear.
Do you have any?
I just confused about it right now.
Well, like I said, you may think of it in the terms of you cross V with B, and you see which direction your vector is. And then you have a scalar multiplied by a vector. So if your scalar is negative, you would flip the direction of this to get the direction.
Yeah, like I said, sometimes I just confused like which way the thing are gonna curve.
Oh, actually the formula is usually shown. So whatever is crossed with what, so you start at this and you curl towards this to give you that. So if it's V cross V, you curl from V towards V. From this to this. Get that.
Cool. Thank you.
Can you give me your A number?
What?
For your A number?
Yes, sir.
Yeah.
Do I need to write down my name?
No, I got it.
Okay, cool. Thank you. This is on the blackboard.
Blackboard.
Yeah, there's
The CS stuff, passing posted CS exam 2. He said we were going to find it in the exam. I mean, assignment error for Blackboard CS. I checked yesterday.
for which class? Physics?
No. CS 104.
For what? For the
Exam. Exam 2.
oh no. I did not check out that. But I found this from
Yes.
this physics.
Okay. Free lecture.
Yeah. No. No, it's
Check one.
no. I mean there's an exam.
Okay.
Previous exam.
Yeah. But I mean,
I think this is the same one.
yeah, this is the same one, but this is from the checkpoint or pre-lecture. This is from the pre-lecture. Yes.